Be doing the last bit of chapter 5, which is the course revision. I'm going to be going through these 4 questions because I think they're the most confusing or strange things that you can find in the sheet. I'm going to be using the course revision question sheet, which you can find under here if you want to follow along. And I'm going to start with question 19. I will not be explaining any formulas or anything in this video. I have 2 other videos that deal with all the theoretical stuff, so you can just look at those. I'm just going to be purely solving questions here. So basic question 19. An 8.2 liter flask contains 2.5 moles of hydrogen, half a mole of chlorine, and enough argon so that the pressure of the argon is 2 atmospheres. The temperature is given to be 127 degrees Celsius. Part A asks us to find the total pressure. Now, of course, total pressure just means you add the pressure of the 3 gases that you have, which are hydrogen, chlorine, and argon. We already have the pressure of argon, so that's not an issue. We do not have the pressure of these 2. The easiest way to find it is to just do PV nRT for each gas. The pressure of hydrogen is going to be equal to the number of moles of hydrogen, 2.5, times R, which is 0.08. Times the temperature in Kelvin. Kelvin is 400. Over the volume, which is 8.2. And you should get the pressure of hydrogen to be approximately 10 atmospheres. You round to 2 significant figures because the pressures that we have here are in 2 significant figures. Then we can talk about the pressure of chlorine. Exact same process. Number of moles of chlorine is 0.5. R is still 0.08, it's a constant. The temperature is 400, and this is 8.2 for the volume. And the pressure of chlorine that we get should be 2 atmospheres. Now, all you need to do is just add them all together, and your total pressure should be 2 plus 10 plus 2, and it will be 14 atmospheres. So this isn't hard, this just needs you to remember that you should use PV is equal to nRT. Part B asks you to find the mole fraction of hydrogen in the flask. Now there are 2 formulas for mole fraction. We would either do the number of moles of hydrogen over the total number of moles, or we would do the pressure of hydrogen over the total pressure. Now we can clearly see we already have the pressure of hydrogen, we already have the total pressure, we calculated both in part A, so we can just use this one and it's a direct substitution. The mole fraction of hydrogen is 10 over 14. And your answer should be 0.714. There's no unit because it's mole fraction, and mole fraction does not have a unit. Now, part C is the part I want to focus on because it involves like combining reactions and ratios and stuff. So part C tells you that you ignite the mixture and this following reaction happens. The reaction will continue until one reactant is completely consumed, and they want us to find the mole fraction of all remaining gases. The easiest way to start this is to take the reaction given and write it down, and write down what we start with. We start with hydrogen and chlorine, and the reaction is meant to give us HCl. Now, to start this, we have to start with the initial reactants. We have 2.5 moles of hydrogen and half a mole of chlorine given to us in the question, and we're going to use these and not the pressure because you can't consume pressure. You consume moles, but not pressure. And we need to figure out which reactant is going to be consumed because we're told that this reaction will continue until either hydrogen or chlorine reaches 0. Now, hydrogen and chlorine, very clearly, they react in a 1-to-1 ratio, which means that obviously, the one that's going to be consumed first is chlorine. There's way less chlorine than there is hydrogen. So chlorine is just going to become 0 first. Hydrogen, it reacts in the same ratio to chlorine, so if we lose 0.5 here, we lose 0.5 here. And we end up with 2 moles of hydrogen left. And we should not forget that this reaction gives us HCl. If you forget this, your entire answer will be wrong. Now, to get how much HCl we receive from this, we have to use the limiting reactant, 0.5. The ratio is 1 to 2. So for every 1, you get 2. For every 0.5, you're going to get 1. So I'm just going to write that here, 1 mole of HCl. Now we have these 3. The last thing we need is the number of moles of argon. We have the pressure of argon, similar to question part A. all we need to do is just PV is equal to nRT. So the number of moles of argon is going to be equal to P, which is 2, times V, which is 8.2, over R, 0.08, times the temperature, 400. And you should get the number of moles of argon when you round them down to be 0.5 moles. Now, after we did this, we can just do a direct substitution into the formula for mole fraction, which we're going to use this one to do it. So the mole fraction of chlorine is very clearly 0 because we have no chlorine left. The mole fraction of hydrogen is what we have left, which is 2, over the total number of moles, which is 2 plus 0 plus 1 plus 0.5. That's 3.5. And we should get 0.571 mole as a mole fraction. We do the same for argon. It's 0.5 over 3.5. The answer is 0.143. And finally, we do the same thing for HCl. It's 2 over 3.5. We get our final answer to be 0.286. I really hope that was clear. Now, moving on, I'm going to be solving basic question 20, which deals with kinetic energy. This question is fairly straightforward. The important part is understanding what the ratios mean. You're given a container with hydrogen and helium gas, and it asks you which will effuse faster and how many times. So, of course, the first thing we need to confirm is that they both have the same kinetic energy. They're both in the same container. This means the temperature has to be the same. A container can't exist at two different temperatures. So same temperature, same kinetic energy, check. So now we can just choose either of the two formulas we have that deal with kinetic energy. For this question, I'm going to be choosing the formula M1 over M2 under a radical is equal to V2 over V1. And the reason I'm choosing this is because we want a ratio of speed, and this will directly give us a ratio of speed. So if we substitute 1 with hydrogen and 2 with helium, and of course keep in mind that these two are swapped numbers, then all we need to do is just directly substitute. The molar mass of hydrogen is 2, the molar mass of helium is 4, is equal to the velocity of helium over that of hydrogen. Cross multiply, and we're going to get that the velocity of hydrogen is equal to 1.4 times the velocity of helium. Now, the way this is read is that the velocity of hydrogen is 1.4 times bigger than the velocity of helium. And if you struggle to understand it this way, then just think of their weights. We can clearly see that hydrogen is lighter, which means that hydrogen has to be faster. And that's why we can clearly say that hydrogen moves 1.4 times faster than helium. And that's just our final answer. I'm going to move on and do basic question 25. There's no solving here. It's all just understanding how kinetic energy works with gases. And what we are given is 5 identical balloons containing these 5 gases. All balloons are at 25 degrees Celsius and 1 atmosphere. Part A asks you which balloon has the greatest mass. The first thing we're going to look at is the fact that they're at the same conditions, same temperature, same pressure. This means that Avogadro's law applies. And Avogadro's law tells us that at the same conditions, the same number of moles exists no matter what the gas is. That means we have equal amounts of each of these gases. And because we have equal amounts, all we need to look at for this is just their molar mass. The one with the higher molar mass is just going to be heavier. So, because number of moles is equal to mass over molar mass. As molar mass increases, this will increase to cancel out. We look at molar mass. The molar mass of C2H6 is 30. The molar mass of SO2 is 64. The molar mass of Ne is 10. That of oxygen is 32. And that of carbon monoxide is 28. So we can obviously see that SO2 is the heaviest gas, and that means the SO2 balloon has the greatest mass. Part B asks us to compare their kinetic energies. This should be immediately obvious. We have the same temperature for all of them. The kinetic energy is the same. Part C, which gas will deviate the most from ideal behavior? Now, if you've watched the ideal behavior video, we know that ideal behavior occurs best when the temperature is high, when the pressure is low, and when the gas is light. Now, all of these balloons are the same temperature and the same pressure, so we can't use these. We could use this. We can obviously see here that our lightest gas is Ne, but they don't want which one goes with ideal behavior. They want deviation. So instead, we're going to look at our heaviest gas, SO2. SO2 is heaviest, which means it will deviate the most. And again, the reason it will deviate is because there's way more forces affecting SO2 than there are in Ne. And finally, part D asks you which gas will effuse fastest. Now, fast just means light, so we look at our lightest gas, it's Ne. Our answer is neon gas. Now I'm going to be solving the last question in this video, which is grid question 1. This question is unique because it deals with pressure over water, but as far as I know, this is the one time this question appears in the entire revision sheet, so you should just know the formula and how it works. We have 20 milliliters of neon gas collected over water. The total pressure is 1.32 atmospheres, and the vapor pressure is 25 milliliters of mercury. Now, they want us to find the number of moles of Ne gas collected. Now, if you don't remember what collection over water is, the way it basically works is you just have a tube where you're collecting the gas, and the tube is immersed in water, and you're just collecting this gas over water. And because the gas has its own pressure, and the water has its own pressure, these pressures are going to interact and they're going to affect each other. We know that the total pressure is 1.32, and that the pressure of the water is given to us in milliliters of mercury, and it's 25. So the only equation you need to know for this is that the total pressure is always an addition of the pressure of whichever gas you have and the pressure of the water. And since they want us to find the moles of Ne, we're going to have to use PV is equal to nRT. And we have all three values except for P. And this is how we find P. So it's a direct substitution. The pressure in total is given to us to be 1.32. The pressure of the gas is what we're missing for our equation. And the pressure of water is in millimeters of mercury, which means we're going to have to convert. It's 25 over 760. Now, if we just take this to the other side and subtract it, the pressure of the gas on its own should be 1.29 atmospheres. From here, all we need to do is just substitute. N is equal to the pressure we found, 1.29, times the volume, which is 20 milliliters. So we're going to do 20 over 1,000 to convert properly. Over R, 0.08, given to us in the equation. And the temperature, it's given to us in Celsius. We're going to add 273, and it'll be 300 Kelvin. From this, your final answer should be something around 1.06 or 1.08 times 10 to the negative 3 moles. The only thing you really need to keep in mind is this equation right here. The total pressure is the pressure of water plus the pressure of the gas. This question appears only once, but you should know how to solve it because it's fairly easy. The applications are always direct. So I really hope this video has helped you guys out. This should be the last chapter 5 video, so, good luck with your exam. Thank you for watching.